Hey, Katie.
Hey, Ben.
So we've talked about neural nets before, and the general concept makes a lot of sense to me, but I'm a little shoddy on the details, and I was hoping maybe we could explore some backpropagation today.
Okay, yeah, sure, let's try it.
You are listening to Linear Digressions. Okay, so as I understand it, and I'm not the data scientist here, neural networks work by kind of simulating the human neurological system. You create these multiple layers of neurons, and you pass a signal, your initial signal, whether that's text or some other kind of input, through all of these different layers, and each layer modifies the input in some way. And then eventually, by the last layer, you get to your answer, whatever that answer may be. Now you might ask, how does that actually happen? Like, these layers can't just magically know what you want at the end. And so what you do is you train the neural network by passing it some labeled data, some data that you have the input, but you also know what the output should be. And you pass it some input and tell it the output should be this, and some more input and tell it the output should be this. And all of the layers in between kind of, this is the fuzzy part, right? They kind of rejigger themselves and optimize themselves so that way for those inputs that you provided, you get those outputs that you told it you should get. And then the idea is if you, let's say you're training on some image data and you're trying to train coffee cups, right? So you've got a bunch of pictures of coffee cups, you pass them all in and you tell the neural network, if I give you this picture, you should say coffee cup. If I give you that picture, you should say coffee cup. And if you train enough of those, you can give it a picture of a coffee cup that it's never seen before, and hopefully it should say coffee cup on the other end. I'd like to talk about the fuzziness in between. Like, how does all that work? How does it know how to tweak its different layers of the neural network to optimize for what you want?
Sure. So the first thing is that calling the middle layers of a neural net, calling them neurons, is being faithful to some of the literature on the subject, and it was certainly faithful to the inspiration. We think of these as layers of neurons kind of in your brain. That was the original inspiration. But they're not neurons, right? They're little computer program bits. And so what they actually are is they're mathematical functions. And so the mathematical function takes some input, some number, and then it produces some output. And usually the way that this actually works is it'll take a number of inputs from a number of different sources. So if we're using the example of a picture, what you do is each pixel in the picture is an input, and then a hidden layer, one of these neuron things, will take inputs from a number of different pixels. So it's getting information from 3 or 4 or 5 or 10 or 100 different pixels all at once. Each of those is going to be a number. So it's reading in 100 numbers. And then those numbers are multiplied by weights to sort of get different contributions from different pixels or different parts of the problem. And then you sum over all of the pixels times their associated weights. You add those all up, and then you pass them typically into something like a logistic function. And then that logistic function is effectively working as kind of a threshold finder almost. And it says, what I'm trying to do is decide whether this neuron is going to fire or not. And if this neuron fires, then it's going to send a signal out to the next neuron that's downstream of it. And then if it doesn't fire, it's not going to say anything. And so then the next layer downstream is going to get its own set of inputs, which are the outputs of the layer that I'm in right now. But the layer that I'm in right now, I'm just trying to decide if my particular neuron is going to fire.
Right, and this is going forward, right? This is not the backpropagation stuff we're going to be talking about. This is just describing, like, how do you reduce a picture with tons and tons, millions of pixels down into a single answer like that. And so these neurons will take chunks of it and then reduce it down to either a 1 or a 0, depending on whether that function decides it should fire.
Yeah, and so the idea is that it does that reduction from all these different inputs. It does that reduction via just a mathematical transformation. And so there's like an equation that you put all these inputs into it, and then it spits out either a 0
and
or a 1.
That's a fixed equation?
Well, so the equation itself is fixed, but the weights that are associated with each of the inputs, those are free to move around. And
Oh.
when you're training a neural net, what you're actually doing is figuring out what weights you want to have on each of the connections between the different neurons in or sometimes called hidden units too, the different hidden units in your
So
net.
when I'm training my neural net, I'm not actually changing the equations that govern how the neural net works. I'm just changing the weights of the different pixels, or I should say the different inputs. Because after that first layer, then all of those neurons go into other neurons as inputs of other neurons. And then those neurons do their thing and then decide to fire or not fire. And you go through multiple layers like that.
Yeah, that's right. So you have sort of a simple basic structure, which is that I have these neurons. They take inputs, put it through a mathematical function. On the basis of evaluating that function, they fire off an output. And then like you said, you have just sort of a daisy chaining of all of these different neurons that get chained together in complicated ways. And so at the base of it, it's actually a fairly simple question, is just, am I above the threshold that it takes to fire this neuron? But especially when there are many layers that are stacked on top of each other, at the end of that, you're going to get some aggregated output, which is going to say, is this a coffee cup or not? Or the value that I predict for this thing that you're trying to model is going to be some number. And how far away is that number from sort of the true value of the model?
So there's an emergent property in a way where the basic operating principles are relatively simple, but when you put it all together, you get something a bit more complex from stacking these things.
I mean, more than a bit more complex. It can be really, really complex, and it's nonlinear, and one of the drawbacks of neural nets is that they can just be really difficult to understand what it is they're doing. And so this was actually a fundamental problem with neural nets for a long time, is they had the idea for neural nets fairly early on. But the question was, how do you figure out which values of the weights are in general going to be giving you answers that are as close to correct as possible for your training cases? Like, how do we take, we have all these weights that are set for all the connections between the neurons, which are basically numbers in a bunch of different equations. And then through this very complicated interaction of all these equations, you get some answer out. That answer is not going to be quite right. And so how do you take the information about how far away this answer is from where you want to be, and take that and feed it back into the neural net so that the neural net then can take steps on the weights. It can change around the weights to get closer to where it wants to be.
Yeah, it's certainly not something you could manually do. Just decide, oh, I'll just tweak this number or that weight, because there's just so much of it and you're not really sure how it's going to impact the ultimate output.
Yeah, and so that's what backprop is. Backpropagation is you're taking the difference between what you call usually your error term, the difference between the number that you got out and the number that you wanted to get out. You take that error and you sort of mathematically push it back through the neural net in the other direction. And since you have all these mathematical functions that are describing the different neurons, you can take derivatives of those functions. And those effectively, I mean, there's a lot of like calculus involved in kind of the chain rule of taking derivatives. But the upshot of it is that you can come up with a mathematical equation that says, what's the relationship between the value of a weight and the error that I get out as a result of that? Like, what's the d error over d weight, if I'm speaking in terms of derivatives. So then once you have that information, you can use it to inform whether you're going to move a given weight up or down and by how much. And so making those adjustments is how you actually train the neural net. So backpropagation is a way of taking the mistakes that you make and learning from them, basically.
Oh, that's really interesting. So from a very high level perspective, not thinking about the math of it at all, what you're doing is you're running something through the neural net, and you know the answer that you want, and that's important. And you look at the answer that you get, you look at the answer that you want, you figure out what the difference is, and then you take the difference and you run it backwards through the neural net to see where your numbers should have been in order to get the answer that you actually wanted, or rather how to tweak them.
Yeah, I would say how to tweak them is maybe a better way of saying it. But yeah, that's all that backpropagation is sort of taking the errors and then propagating them backwards through your neural net. And then what you do is you have a neural net that's hopefully a little bit closer to where you actually want it to be. And then you take your training data and you run it through again, and you see how close you are. and hopefully you're a little bit closer, but there's still going to be some error term, and then you take that error term and you propagate it back, and then you do it again, and then you kind of just slosh back and forth, and you asymptotically, hopefully, if it's converging, it will approach the set of weights that are optimized over the whole neural net. So your neural net then has been trained. It has sort of like the best possible set of weights for all the different test cases that you've seen. Or I should say for all the different training cases.
And at the end of the day, it can successfully identify a coffee cup.
These days, yeah, their neural nets are the state of the art for things like image recognition, also speech recognition, things like that. Yep. So that is kind of, in a nutshell, the magic of backpropagation. It's the thing that underlies all these neural nets. Do they feel a little less mysterious to you now? Is the magic still there?
The magic is still there, but yeah, they definitely make a little bit more sense. It feels a little bit less magical, but it still is just, I mean, it's just something that we're not evolutionarily predisposed to understand. So my brain still grapples with it a little bit. Neural nets in general, I suppose.
As an editorial, just aside, neural nets seemed like real black magic to me for a long time. I'm starting to learn a little bit more about them now, and they feel less mysterious. I feel like I at least understand the individual pieces of them better. But yeah, like we said, that's one of the things that's really tough about neural nets is that when you get, even if the building blocks are kind of simple, when you assemble them into these networks and they start to feed into each other in ways that you can't keep track of everything all at the same time, yeah, they can be, they can get big and complicated and things like that. But I found them to be, the more I study them, the more I feel like I understand them, which is nice. They do reward dedicated attention.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.